Hello and welcome to the session FEM analysis, and we can continue to the next step, which is defining the FE boundary conditions. At this point, we don't need a solid part or a mesh or nodes or anything. The definition of our boundary condition is purely geometrical, and later in the assemble model, those nodes will be selected. So let's start with the force I already talked about. We want to apply it to the start node of those connector elements. And I also prepared a vector here, which has a factor of 1000 and points in negative z direction. So I will just type in force to get the force component on the canvas and connect all the inputs. Okay, lastly, we plug in the vector, and as you can see, we defined our force. All right, so now we also have to define a support, because right now our model would behave like in space and just float off in negative z direction, because this is where the force is pointing to. So now we want to support our model and fix this surface. If you get the support component, give it a name, enter the support surface, again a tolerance, and now we have defined that all nodes that lay within this surface or within the tolerance to the surface of the model will be fixed in all 6 degrees of freedom. You can use these toggles here to select or deselect degrees of freedom. And now we have a force and a support, and these are 2 loads, which we will now combine together into a load step. The load step can be used for a static mechanical simulation, and we will give it a name. It's called load step. Plug in both loads, and now we have defined our load step and already finished step 3 of the FEM setup. We are now ready for the last step of this lesson, which is running the FE setup. And before we can do that, of course, we have to first assemble or construct the FE model. And for that, we need the construct model component. We plug in the name of this model, then the different parts, the rigid connector elements, our load steps, and you could also define a tolerance. So all nodes within this tolerance would be merged. In our case, we don't need a tolerance. Yes, so now you can see already we have our model defined here, and here you can now see the connector elements being displayed. And now if you are not happy with the location of the start node, you can go back to the RBE element section, blend in that start node, select it in the viewer and drag it to a different location. All right, let's go back to our 4th step. So here we have now our model defined. If you don't have an Altair license available, here is an internalized model which you can use for the next step. So now we will actually run the model. However, you could also use this constructed model for a topology optimization, for example. And if you drag this wire, you get the OptiStruct solver suggested, and now this is running. It's an external solver that's running through, and the result is our FEM model. the load steps and how the model responds to the loads. If you plug the successful output in here, you read true, which means our calculation has been successful. If there's an error or a warning, you will not get true, but probably false, and then you can also read about what the issues are if you plug in the info output into the panel. Before we will take a look at the model with the model view component, I will just press Ctrl A to select everything and hide everything selected so that we don't have different parts showing in the viewer. Okay, so let's connect the model into the model view. And as you can see, it runs through and gives us this nice look at the cantilever beam. And here you have lots and lots of settings to choose from to adjust this view. So right now we are looking at the load step and the element stress. We can also check out the nodal displacement instead. Then we can only look at the displacement in one direction, or we go with the magnitude of the displacement. Also, there's a displacement scale which I set to the maximum because it makes it easier to actually see something, but of course you can go with a more realistic view. And then also here you have the result bound for this color scheme, where your color scheme bound starts and end can be defined here. And then also you can choose from different color maps. I like the rainbow one. Then we have this isoluminant, cool to warm. This is very much a personal preference. Okay. And then also here you can go into the legend type, have no legend, discrete legend, change the number of colors, change the font size, change the decimal places, the significant places, very much, adapt this to your personal needs and how you prefer to look at your results. Okay. And now if we go back again, you could select our point here again, the start node, and if you now drag it to a different location, I am going with a more drastic change here, the whole DNA will recalculate. We are now already at the solver, and then you will be able to see the updated model view. In this session, we went through all the steps that are needed to set up a FEM model and analyze it in our software. You are now able to take this knowledge and transfer it to analyze your own products.